We present a method for end-to-end training of deep visuomotor policies that map camera images and robot configuration directly to motor torques. Our convolutional neural network policy has 7 layers and 92,000 parameters. We vary the position of the target in each task, perform insertions with only a millimeter of tolerance, use a variety of different grasps that must be determined from images, and screw bottle caps onto bottles. Here, the policy must determine the distance to the rack from monocular images to successfully place the hanger. The policy generalizes to racks with clothes, without additional training, as well as small objects on the hanger such as towels. Here, the robot inserts a block into a shape-sorting cube. The policy was trained with the cube in the robot's arm, but generalizes to the cube sitting on a table. The hammer task is performed with various grasps, which the robot must identify by watching the toy hammer and its own gripper. The policy generalizes to placing the hammer under the nail in the presence of clutter. The bottle task requires screwing the cap onto the bottle. This visuomotor policy also generalizes to the presence of clutter in various positions. The policies use input from a monocular camera to complete the task. Camera images, together with the robot's configuration, are processed at 20 Hz to produce motor torques. For the hammer task, the policy must infer both the position of the target and the current grasp, while the bottle task requires precisely localizing the bottle opening and rotating the wrist to tighten the cap. Here we show a variety of visual generalization experiments. The inch sets show the camera images that are fed to the policy. The hanger policy can handle different hangers and large objects that cover part of the view. The insertion task succeeds in the presence of new objects in the background, and can even insert the block when the cube is held in a person's hand. The hammer task can also be done with an arm in the scene, as can the bottle task. Here, the robot follows a moving target. The target did not move during training. When we cover the monocular camera, the robot is unable to localize the target or determine its grasp. The policy attempts to reach an average target position. When the scene is revealed again, the policy makes a last-ditch attempt to recover. This indicates that the camera images are actively used by the policy. The trained policy can fail when we change the mass of the hanger and cover large parts of the target object, or when the background changes dramatically, altering the brightness of key features such as corners. Here, the gray shirt appears similar to the robot's gray arm. And here, the policy attempts to recover from perturbations, which put it in states that are too different from training.